Now let us find the Fourier transform for e power minus at sine omega naught t u of t. So I can write this function as e power minus at. Instead of sine omega naught t, I have e power j omega naught t minus e power minus j omega naught t divided by 2j into u of t, right? Now let me simplify, let me separate these things. So now I can write it as Fourier. If I take a Fourier transform of the above function, how can I write it? I can write it as Fourier transform of e power minus at into u of t I have a multiplicative factor 1 by 2j, and what I have e power j omega naught t, e power j omega naught t. Similarly, I have another term, right? That is Fourier transform of 1 by 2j e power minus at u of t into u of t, and there is a negative sign here, so I will have a negative sign here, right? And e power minus j omega naught t. Now, what is the Fourier transform for e power minus at into u of t? We have already found this one, right? Single-sided exponential. The Fourier transform is nothing but 1 by a plus j omega. Right? That is the Fourier transform for e power minus at into u of t. Now I am going to introduce a phase shift in my time domain signal. Phase shift in time domain signal is nothing but it has a corresponding frequency shift in Fourier domain. So e power minus at into u of t into e power j omega naught t. What will the Fourier transform be? Fourier transform is going to be 1 by a plus j into omega minus omega naught. So if I have a minus sign here, I'll have plus sign here. So I will substitute that. So 1 by 2j is a constant. And for this, the Fourier transform of e power minus at u of t e power j omega t is 1 by a plus j into omega minus omega naught minus, for this one, for the second term it is 1 by a plus j into omega plus omega naught, right? Now I can simplify this, right? How can I write this thing? I can write it as 1 by the real term and the imaginary term, or let me just simplify it. So how can I simplify? It is 1 by 2j if I simplify it, I'll get 2j omega divided by a plus j omega whole square a plus j omega whole square plus omega naught square plus omega naught square. Now 2j and 2j cancels, so I have omega naught divided by a plus j omega whole square plus omega naught square. So similarly, you can take a cos signal here and find out the Fourier transform, right? Then let's move on to the next problem. Here in this problem, we are already given the time domain signal and its corresponding Fourier transform. Now what are we asked to do? We are asked to find the Fourier transform of g1 of t. For g of t, they have given the Fourier transform. We have to find the Fourier transform for g1 of t. So let us find a relation between g of t and g1 of t. So what is the relation between g of t and g1 of t? If you look at them, g1 of t is nothing but a folded version of g of t, right? g1 of t is equals to g of minus t, right? We are just folding g of t. So whatever is on the left side will come onto the right side. So that is the same thing here, g1 of t. So what will be the Fourier transform for time reversal when you reverse it? So g of minus t, what will be the Fourier transform? What will be the Fourier transform? It is going to be g of omega by minus 1, right? How did we get this? We are taking scaling. What is the scaling formula? Scaling factor. G of at will have the Fourier transform. G of at will have the Fourier transform 1 by mod a into g of omega by a. Instead of a, we have negative 1. So 1 by mod negative 1 is 1. Then g of omega by minus 1. So instead of omega, so this can be further simplified into g of minus t as the Fourier transform g of minus omega. So in place of omega here, if I substitute minus omega, I will get the Fourier transform for g1 of t. So the Fourier transform will be 1 by minus omega square is nothing but omega square into e power minus j omega minus j into minus omega. So this becomes plus omega and e power minus j omega minus 1. So this is my Fourier transform for g1 of t. Now similarly, I'll find Fourier transform for g2 of t. So how is the g2 of t function looking like? It is just the shifted version of g1 of t, right? I am shifting g1 of t to the left hand side. That is when I'll get g2 of t. So g2 of t is nothing but g1 of t. Which direction am I shifting? I'm shifting it into left hand side. Left hand side means I should take plus sign. Then by how much am I shifting? Whatever is there at 0 in g1 of t, where is it now? It is at minus 1. So I'm shifting by 1 unit. So 1 unit, right? So this is my relation between g2 and g1. So what is my time shifting property? G of t minus b, time shifting. What is the Fourier transform? Fourier transform is going to be g of omega into e power minus j omega d, right? Now g1 of t plus 1 means in place of b I have minus 1, right? Now what is the Fourier transform? It is nothing but g of omega into e power j omega. B is minus 1, so minus into minus is plus 1, so e power j omega. So whatever my g of omega, so g1 of omega, right? g1 of t, so g1 of omega. This is my g1 of omega here. So whatever my g1 of omega is there, I should just multiply it with e power j omega. So if I multiply it with e power j omega, what will I get? 1 by omega square. I have to multiply this with e power j omega, right? E power j omega. I'm just multiplying it. So now e power minus j omega into e power j omega is 1 plus j omega, e power minus j omega into e power j omega, again 1 minus 1 into e power j omega is e power j omega. So this is my Fourier transform for the second signal. So here we are just finding the relation between these two signals. How are they related? The first one was just the time reversal relation. So in place of a I have minus 1, so I just use this formula here. And the second signal is just the shifted version of the first signal. So I use the time shifting property. So we used time scaling as well as time shifting properties in this example. Now we'll find the Fourier transform of this function. Now we are given a function in its mathematical representation, right? The function is given in its mathematical representation. Now we'll have to find the Fourier transform of this function. So let us just draw this function. If I draw this function from minus 1 to minus 2, what is my value? It is 1, right? It is 1. From minus 1 to plus 1, it is 2. Minus 1 to plus 1, it is 2. And from 1 to 2, it is again 1, right? And all other values, it is not given, so we assume it is 0. Other values, it is 0. So this function, I will try and represent it as sum of two different functions. Right now I can take a function from minus 2 to minus 2 to plus 2 with amplitude 1, and another function from minus 1 to 1 with the amplitude 1. If I add these two functions, am I getting the original function? So from minus 2 to plus 2, it is 2, and here from minus 1 to 1, it is 1. If I add these functions, I will just overlap this function here, right? So from minus 1 to plus 1, I have 1 here and I have 1 here. If I add 1 plus 1, it is 2. So from minus 1 to plus 1, it is 2. And similarly from minus 2 to minus 1, here I have 1 and here it is 0. In the first signal I have amplitude 1, second signal amplitude is 0. So 1 plus 0 is 1. Similarly from 1 to 2, the first signal the amplitude is 1, second signal the amplitude is 0. 1 plus 0 is 1. So I can represent my given function f of t as sum of two different functions. Now I'll take Fourier transform of this function, right? Fourier transform of this function, Fourier transform of this f of t is nothing but Fourier transform of this function here, so minus 2 to 2 plus Fourier transform of the second function, right? It is the Fourier transform of two rectangular functions. So let me calculate the Fourier transform. What is the Fourier transform of a rectangular function? Rectangular function a tau sampling of omega tau by 2, right? Here tau is the pulse width and the a is amplitude. For this first signal, what is a? A is 1 and tau is equals to 4, right? A is 1, tau is 4. So it's going to be 4 sampling omega tau is 4, right? 4 by 2, so 4 sampling in 2 omega. And here this one, a is 1 and tau is 2, so I have 2 sampling of omega, right? I'll add these two, so this is my final answer. That is my Fourier transform. So these are different problems you can practice. This is the triangular function. This is the triangular function. We already found this in one of the previous slides. And this is the cos e power minus at cos omega naught t u of t. So we have found for sine version, sine omega naught t u of t in the previous slide, one of the previous slides. So this is the cos version. It is very similar to that. And this is another problem. You can try this for practice. And now we'll look at inverse Fourier transform for f of omega equals to 1 by 2 plus 1 by 2 signum of omega. So I need to find the inverse Fourier transform. So that is, I have to find f of t, right? So f inverse of 1 by 2 plus 1 by 2 signum of omega. Now I'll separate the Fourier transform. I'll separate the inverse Fourier transform. So that will be f inverse of 1 by 2 plus f inverse of 1 by 2 signum of omega. Now we know the Fourier transform of del of t is 1, right? Fourier transform of del of t is 1. Now if I multiply by 1 by 2 on both sides, it's going to be like this. Now what does this mean? Fourier transform of 1 by 2 del of t is 1 by 2. That means inverse Fourier of 1 by 2 is 1 by 2 del of t, right? So inverse Fourier of 1 by 2 is 1 by 2 del of t. Then signum of omega, right? So for this we'll find the inverse Fourier transform. So first, what is the Fourier transform of signum of t? Signum of t Fourier transform. Fourier transform is 2 by j omega, right? 2 by j omega. Now I'll apply duality to this Fourier transform pair. So what do I get? I get 2 by jt will have Fourier transform 2 pi signum of minus omega, right? 2 pi jt signum of minus omega. Now signum of omega is something like this. Signum function is like this. If I take the time reversal of this thing, how will it look? It will look like this, right? Time reversal or folding. So both of these are exactly opposite in amplitude, right? So this is an odd function. So how can I write this one here? Signum of minus omega, it is nothing but minus signum of omega. So minus 2 pi signum of omega, right? Now I will take this 2 pi to the other side, minus 2 pi to the other side. What will happen? 2 divided by minus 2 pi j t. The Fourier transform is going to be signum of omega. So simplifying, what do I have? This j, if I take it to the numerator, it becomes minus j. So minus and minus cancel. I have j by pi t. So the same thing I'll write here. I have a half coefficient here, so that comes like that, and into j by pi t, right? J by pi t. So this is my inverse Fourier transform, that is f of t. Okay, this is how we can find inverse Fourier transform. Now find the inverse Fourier transform of del of omega and del of omega minus omega naught. So we know Fourier transform of del of t. Del of t is 1, right? Now if I apply duality, it will be 1 will have the Fourier transform 2 pi into del of minus omega. Del of minus omega is an even function. Del of omega is an even function, so I can make it plus. So if I get the 2 pi to the other side, I'll have 1 by 2 pi with the Fourier transform del of omega. So my inverse Fourier transform for del of omega is nothing but 1 by 2 pi, right? Now if I want to find the inverse Fourier transform for del of omega minus omega naught, I have to apply frequency shifting. To this transform pair. So if I apply frequency shifting, my right hand side becomes del of omega minus omega naught, right? I'm shifting by omega naught. So what will be my time domain signal? 1 by 2 pi. I should introduce a phase shift, e power j omega naught t. So this will be my inverse Fourier transform for del of omega minus omega naught. So here we are using frequency shifting and duality. Now inverse Fourier transform of f of omega. F of omega is given. So let me find the inverse Fourier transform. Now I first take this omega square to the other side. So what will be my left hand side? It is omega square into f of omega square into f of omega, that is equal to 15 e power minus 3j omega minus 10 e power minus 2j omega minus 5 e power minus j omega 5, right? Now I'll introduce a negative sign here, or a negative sign. Yeah, I'll introduce a negative sign. So I'll introduce a negative sign here also. I'm just multiplying it by negative 1. So minus omega square. How can I write minus omega square? Minus omega square is nothing but j omega whole square, right? So instead of minus omega square, I can write j omega square. Here I can write j omega square into f of omega. On the right hand side, I'll have the same thing, right? I'll have the same thing. Now, what is this? What do I have from what I will have from time differentiation? From time differentiation property, I have d by dt of f of t as the Fourier transform j omega into f of omega. Now, if I have d power n by dt power n into f of t, then I'll have j omega whole power n. Now when n is equal to 2, what do I have? I have d square by dt square f of t, the Fourier transform j omega whole square into f of omega. Right? If I take the inverse Fourier transform, now I'll take the inverse Fourier transform on both sides. The inverse Fourier transform for my left hand side is nothing but d square by dt square, d square by dt square into f of omega, that is equal to inverse of the right hand side. What will be the inverse of right hand side? So minus 15 f inverse of e power minus 3j omega. So let me see what is the inverse for what is the Fourier transform for 1, or sorry, what is the Fourier transform for del of t? Del of t Fourier transform is 1, right? Now if I introduce a phase shift on the right hand side, that is e power minus j omega t naught, right? If I introduce a phase shift, what will happen to my time domain signal? It will be a shifted version, that is del of t minus t naught, right? So here my Fourier transform signal is e power minus j omega 3. So in place of t naught I have 3. So my time domain signal, corresponding time domain signal will be del of t minus 3. So del of t minus 3 plus 10 into, now instead of t naught I have 2. So that's going to be del of t minus 2, and instead of t naught this time I have 5. So that is del of t minus 5, right? I made a small mistake here. Please correct. The inverse Fourier transform is d square by dt square into f of t, not f of omega. This is f of t. Now I need to find f of t. So what I can do, I'll just integrate it once. Let me integrate once. If I integrate once, I'll have d by dt of f of t. What is integral of this? Is what? This is a unit impulse function, right? Delta impulse function. Integral of impulse function is nothing but a unit step function. So that is minus 15 u of t minus 3 plus 10 u of t minus 2 plus 5 into u of t minus 5. Right, this is after one integration. Now if I integrate one more time, this differentiation will get cancelled. So I will be left with f of t equals to, what is integral of unit step? Integral of unit step is a ramp function, right? We have the relation between unit step, ramp and impulse. When you differentiate a ramp signal, you will get a unit step, and when you differentiate a unit step, you will get a impulse function, or a delta function. Now we had a delta function, we integrated it to get a unit step. Again we are integrating it, and now we will get a ramp function. So minus 15 ramp r of t minus 3 plus 10 r of t minus 2. Ramp function is just represented by r, right? Denoted by r. Then 5 r of t minus 5. So this is my f of t. So that is my f of t. So this is how we can find the inverse Fourier transform of the given signal. Now here we are given a graphical representation of f of omega. Now for that also we need to find the inverse Fourier transform. So first I'll write f of omega in terms of an equation. What is f of omega? It is 2 into what do I have here at minus 2 omega naught? I have an impulse, right, with a strength 2. So 2 into impulse delta of omega at minus 2 omega naught. So it is going to be plus 2 omega naught, and 2 omega naught also I have a impulse, right, plus with the same strength again 2 into delta of omega minus 2 omega naught, right, plus I have one more impulse function at 0. So 2 into delta of omega. So I have completed 3 different impulses. Now I have another 2 different impulses. So plus 0.5 is the strength. 0.5 is the strength. And I have 2 impulses, one at omega naught and the other one at minus omega naught. So del of omega minus omega naught plus del of omega plus omega naught. So that is equal to, now I have to find the inverse Fourier transform. So I'll apply inverse Fourier transform on both sides, right? On both sides. So inverse Fourier transform of f of omega is f of t. Now I have 2 inverse Fourier transform of del of omega plus omega naught. that we have to find. So first, what do we find here? Let me take the Fourier transform of 1, right? Fourier transform of 1. What is Fourier transform of 1? It is 2 pi del of omega, right? Now I'll get the 2 pi to the left side. So 1 by 2 pi will have Fourier transform del of omega. So if I apply frequency shifting here, I'll have 1 by 2 pi, 1 by 2 pi e power j omega naught t will have the Fourier transform del of omega minus omega naught, right? So del of omega minus omega naught form is here. So the inverse Fourier transform of that will be 1 by 2 pi e power j omega naught t. In the first case, omega naught is nothing but minus 2 omega naught, right? There's a negative symbol here. So it is minus 2 omega naught. So inverse Fourier transform of that is going to be 1 by 2 pi, 1 by 2 pi e power minus j 2 omega naught t plus 1 by 2 pi e power j 2 omega naught t inverse Fourier of delta of omega. Inverse Fourier of delta of omega is what? 1 by 2 pi. So 2 into 1 by 2 pi plus 0.5 into inverse Fourier of delta of omega minus omega naught plus delta of omega plus omega naught, that is e power j omega naught, sorry, 1 by 2 pi is there, right? So 1 by 2 pi e power minus j omega naught t plus 1 by 2 pi e power j omega naught t. Now e power j theta plus e power minus j theta, what is it? It is nothing but 2 cos theta. So what I can write, this I'll get the pi common, I'll get it outside, 2 by pi, and what am I left with inside? E power minus j theta plus e power j theta by 2, right? So that is nothing but cos theta. What is theta? Theta is 2 omega naught t, cos theta. Then 2 and 2 gets cancelled. I have pi, 1 by pi. I have 1 by pi. And then finally here e power j theta plus e power minus j theta by 2. So here I have 1 by 2 pi in common and multiplied by cos omega naught t. So this is my final answer. Now I have to find the inverse Fourier transform of x of omega, which is in the form of j omega plus 2 plus j omega by 2. So what I can do here, so let us see. Now if I add 2 and subtract 2 here, so how can I write x of omega now? How can I write x of omega? X of omega is equal to 2 plus j omega by 2 plus j omega whole square plus or minus 2 by 2 plus j omega whole square, right? Just cancel. So what am I left with? I am left with 1 by 2 plus j omega minus 2 into 1 by 2 plus j omega whole square, right? Now we know e power minus at u of t, right? It has the Fourier transform. It has the Fourier transform 1 by a plus j omega. So when a is equal to 2, my right hand side is 1 by 2 plus j omega. So the inverse of that is e power minus 2t u of t. Now let me use frequency differentiation here. I will use frequency differentiation here for this. So what will happen? According to frequency differentiation, d by d omega of f of omega is the Fourier transform, and the corresponding what is the corresponding time domain signal? Corresponding time domain signal, if you look at the frequency differentiation, here the corresponding time differentiation is corresponding time signal is minus jt into f of t, right? So we'll do that. So minus jt into f of t. Now I'll apply frequency differentiation for this Fourier transform pair, d by d omega of 1 by a plus j omega. So what is that? U by v formula, right? U by v formula. So a plus j omega whole square, then a plus j omega into differentiation of 1, that is 0, minus 1 into differentiation of a plus j omega, that is j, right? And on the left hand side I have minus jt into f of t, that is e power minus at into u of t. So minus j and minus j gets cancelled. So what do I have? T into e power minus at u of t has the Fourier transform 1 by a plus j omega whole square, right? This is the form I have, 1 by a plus j omega whole square. So now I'll apply inverse Fourier transform on both sides. Inverse Fourier transform on both sides. So inverse Fourier transform of x of omega is x of t that is equal to inverse Fourier transform of 1 by 2 plus j omega. Here in this Fourier transform pair, I'll just substitute a is equals to 2. So my right hand side is 1 by 2 plus j omega. So what will be my left hand side? It is e power minus 2t into u of t, right? Minus 2 into, now in the last equation, last Fourier transform pair here, let me substitute a equals to 2. A equals to 2. So on the right hand side I have 1 by 2 plus j omega whole square. 1 by 2 plus j omega whole square. So the corresponding time signal is t into e power minus a to u of t. So t into e power minus a is 2 t u of t. So this is my inverse Fourier transform for x of omega. X of omega. Now let's move on to the next problem. Inverse Fourier transform of x of omega. Now my x of omega is something like this. So what I will do, I will factorize my denominator. That is, instead of 7j omega, I can write 3j omega plus 4j omega. I can factorize it. When I factorize it, I will get my denominator equal to j omega plus 3 into j omega plus 4. Now I'll do partial fractions on this. Partial fractions. So I'll write this as a by j omega plus 3 plus b by j omega plus 4. Right? This is how I will do the partial fractions. Now for partial fractions, I need to find the value of a and b. I need to find the value of a and b. Now let me cross multiply or take the LCM on the left side. If I take the LCM, on the left hand side I have j omega plus 3, on the right hand side I have j omega plus 3 into j omega plus 4. Now if I cross multiply, a j omega plus 4a plus b j omega plus 3b. This is my numerator. Now I'll compare the coefficients of the constants and j omega terms with the corresponding coefficients. So what will happen? I will take a plus b, my coefficients of j omega, that is equals to 3, and 4a plus 3b, that is equal to 4a plus 3b, that is equal to 14. Now I'll multiply this first equation with 4. So 4a plus 4b equals to 12. Now if I do subtraction, I have 3 minus 4 minus b is equals to plus 2. So b is equals to minus 2, and then a is equals to, if I substitute minus 2 here, a is equals to 3 plus 2, that is 5. Right? A is equals to 5. Right? Now I'll substitute b and a value in this equation. I will arrive at this equation. A value is 5 and b value is minus 2. So the negative sign here. Okay. Now this is the standard form we know, right? What is the standard form? e power minus at u of t. The Fourier transform is 1 by a plus j omega. Now in place of a, what can I put? I can put in place of a 3, right? If I put 3, I will get the inverse of the first term, and if I put 4, I'll get the inverse of the second term, right? So here I'll have 5 is common, sorry, 5 is the constant, and Fourier inverse of 1 by 3 plus j omega, that is nothing but e power minus 3t into u of t minus 2 in Fourier inverse of 1 by 4 plus j omega, that is e power minus 4t into u of t, right? So that is my final answer. So this is how we perform partial fractions. This is the formula for partial fractions. You can follow this method or the method we have discussed in this slide just by cross multiplying. So this one you can write this as j omega plus 3 by j omega plus 3 whole square plus 4 by j omega plus 3 whole square. We have discussed a similar problem already 2 slides back. So the same procedure you can follow and you will get this answer. This is the answer for, this is the inverse Fourier transform for the given Fourier transform. Now we'll see how we can perform convolution of two different signals x1 and x2 using Fourier transform. According to Fourier transform convolution property, what do we have? x1 of t convolved with x2 of t will have the Fourier transform x1 of omega into x2 of omega, right? So what do we have to find in this question? We have to determine convolution of x1 of t and x2 of t. This is what we have to find out. So how can we find out this? We can multiply the individual Fourier transforms and find an inverse for the final Fourier transform. So what is my x1 of omega? x1 of omega is equals to, this is in the form of e power minus at into u of t. So my Fourier transform for that will be 1 by a plus j omega. So 1 by 2 plus j omega, and x2 of omega is going to be 1 by 6 plus j omega, right? So this is the x of omega. X of omega is nothing but multiplication of my x1 and x2. So 1 by 2 plus j omega into 1 by 6 plus j omega. Now I'll write this as partial fractions, that is a by 2 plus j omega plus b by j omega plus 6. Now cross multiplying, I can find a and b. A value comes to be 1 by 4 and b value is minus 1 by 4. You can verify this. Now I substitute a and b values in my x of omega, right? And then I can just take an inverse of x of omega. If I take this inverse of x of omega, I'll have my x of t as nothing but convolution of x1 of t and x2 of t. So inverse of x1 of omega, x of omega is 1 by 4 inverse of 1 by j omega plus 2 minus 1 by 4 into Fourier inverse of, there is no b here, this is just 1. We have already substituted b value. So that is inverse of 1 by j omega plus 2 is e power minus 2t u of t, and inverse of 1 by j omega plus 6 is e power minus 6t u of t. This is the final answer. That is how we will perform convolution of two time domain signals using Fourier transform. If you use the traditional convolution procedure which we discussed in the first unit between two different time functions, e power minus 2t u of t and e power minus 6t u of t, this is the answer you will arrive at. That is very complicated. Using Fourier transform, the procedure becomes very simple. This is one of the advantages of Fourier transform we discussed in the first slides of Fourier transform unit 2.